Hello everyone, welcome to the channel. In today's video, we'll be learning some solving techniques for recurrence relations. But before diving into the solving, let us understand some terms related to recurrence relations. First of all, what is a recurrence relation? It is an equation that represents terms of a sequence as a function of the preceding terms. You can see the examples on the screen. Now, what is the order of a recurrence relation? Number of preceding terms required to define the new term is known as the order of the recurrence. For suppose if you consider this, which is an AP, the nth term is defined using the n-1th term. Even here, which is a GP, the nth term is defined using the n-1th term. Therefore, it is a first order recurrence. But here, the nth term is defined using the n-1 and n-2 term. Therefore, this is a second order one. The same follows for the next example. Similarly, how many our preceding terms use, that will be the order of the recurrence. Now let us define if a recurrence is linear or non-linear. If the exponent of a sequence terms is 1 and the terms are not in multiplication with each other, then the relation is linear, else non-linear. Example, an is equal to an minus 1 times an minus 2 plus k. Here, since an minus 1 and an minus 2 are in multiplication with each other, therefore this equation is non-linear. But here the terms are not in multiplication with each other, and next the exponent of each of the terms is 1. Therefore this recurrence is linear. Now let's define homogeneity of a recurrence. Homogeneity is the exclusive property of linear relations. If the equation, consider this linear recurrence relation f1 n a1 plus f2 n a2 so on till fn an is equal to g of n. If g of n is equal to 0, then this recurrence is said to be homogeneous. If g of n is not equal to 0, then non-homogeneous. Let us take some examples to understand this better. For suppose if you consider AP, an minus 1 is equal to d. Let's say d is not equal to 0. Now if you compare it with this equation, you can say that g of n is equal to d. Now since g of n is not equal to 0, this recurrence relation is non-homogeneous. But on the other hand, if you consider a GP, here again if you take this to the LHS and compare, you will get g of n equal to 0. And since this is a linear relation, therefore it is homogeneous. Now let's see if the constant and variable type. If any of the fi of n, where I belongs from 1 to n, is not a constant, then coefficient is variable, else constant. For suppose you consider this an minus r an minus 1 plus d equal to 0. This is a non-homogeneous recurrence relation as we have discussed. And since r is a constant, and also here if you take 1 is a constant, therefore we'll add something with constant coefficient. If it's not r and it's something of the form like f of n, n square or n cube or anything like that, then we would have written variable coefficient. Hope you understood. Now let's move on to solving some recurrences. Let's start with the basic ones. Here an is equal to f of n an minus 1, where n is greater than or equal to 1 and a naught is equal to k. Here an is equal to an minus 1 plus f of n is greater than or equal to 1 and a naught is equal to k. These both rely on the same idea, which is nothing but a telescopic product and telescopic sum. Let's see how we do that. For in the first part, I'll divide with an minus 1 on both sides. I'll get an by an minus 1 is equal to f of n. Now what I'll do is, I'll take product on both sides. product from I equal to 1 to n ai by ai minus 1 is equal to product from I equal to 1 to n f of I. Now if you expand this, you can see that it is looking something like this. And so until a1 by a0 is equal to product from I equal to 1 to n f of I. Now you can see that the intermediate terms are getting cancelled. It will be cancelling till we reach a1, and we will be left with an is equal to a0 times product from I equal to 1 to n f of I. This is the closed form solution of an for this recurrence. Now if you see the other one, an is equal to an minus 1 plus f of n. Now what we'll do is we'll subtract with an minus 1 on both sides. Now again what we'll do is instead of product, we'll apply summation this time. Summation I equal to 1 to n ai minus 1 is equal to summation from I equal to 1 to n f of I. Now again if you expand this, it will look something like an minus 1 plus an minus 1 minus an minus 2, so on till a1 minus a0. Again you can see that the intermediate terms are getting cancelled. This cancellation will happen till a1, and on the RHS you will be having I summation from I equal to 1 to n f of I. From here you get the solution for an as a0 plus summation from I equal to 1 to n f of I. This is the closed form solution for an. I hope everyone understood. Now let's move on to a bit more complicated ones. Here we are given an is equal to f of an minus 1 plus g of n. Now here neither we can divide with an minus 1 and do a product, or take it to the subtract and do the summation. Neither of them works since we have a f of n here. Now in order to deal with this, what we'll do is we'll try to convert this into a form that we have dealt with before. And in order to do that, we'll do a manipulation. We'll define a new sequence, call it Pn, as f of 1 times f of 2, so on f of n. Now what we'll do is we'll divide with Pn on both sides. An by Pn is equal to an minus 1 times f of n divided by, instead of Pn I am writing the full form, f of 1, f of 2, so on till f of n plus g of n by Pn. Now you can see that fn is getting cancelled. If fn gets cancelled, the last term will be f of n minus 1, which means we will be left with Pn minus 1. An by Pn is equal to an minus 1 by Pn minus 1 plus g of n by Pn. Now we will define a new sequence. Vn is equal to an by Pn. We will get Vn minus 1 is equal to Gn by Pn. Now again this is a telescopic sum, and again if we add the terms, and we'll get Vn minus V1 is equal to summation from I equal to 2 to n g of I by pi. And if we substitute an in place of this vn, we'll get an is equal to pn times a1 by p1 plus summation I equal to 2 to n g of I by pi. Now this is the solution. So this is how we convert anything of this form to a form we know, like the telescopic sum, and we deal with it. Let's see some more types. Now here we have an is equal to c1 times an minus 1 plus c2. N is greater than or equal to 2. a1 is some constant. And some c1 and c2 are constants, and c1 is not equal to 1. Now here you can say that even in the previous one, if you substitute fn and g of n to be constant functions, you'll have the same recurrence. What I'll do is, I'll define a new sequence. an is equal to, call it bn plus lambda, where lambda is some arbitrary constant which will be our main constraint to solve this question. Now if I substitute this definition of n, we'll have bn plus lambda is equal to c1 times bn minus 1 plus lambda times c1 plus c2. If we take the lambda to the other side, you get bn is equal to c1 times bn minus 1 plus lambda times c1 minus 1 plus c2. Now the purpose is, now if I can, since lambda is of my choice, I can choose it to be any value. I'll choose lambda such that this whole expression will turn out to be 0, so that I'll be left with bn is equal to c1 times bn minus 1, which I know how to deal with by doing the telescopic product. So in order to make this 0, I will choose lambda is equal to c2 by 1 minus c1. This is why we took c1 is not equal to 1, since the denominator will turn undefined. And also if c1 is equal to 1, this is nothing but an AP, which is obvious to solve. Now if I substitute this lambda, I'll get bn by bn minus 1 is equal to c1. I'll get bn is equal to b1 times c1 power n minus 1. Now what I can do is I'll substitute an in place of bn to get a solution for an. This is how we deal with this. I hope everyone understood. Now let's move on to nonlinear recurrence relations. Now this is nonlinear because if you take the denominator to the other side and multiply, you'll get an times an minus 1 in a term, which makes it nonlinear. And also n is greater than or equal to 2. an is not equal to 0 because it's a trivial solution. And also we don't want any of alpha, beta, gamma to be 0. If alpha is 0, an will be 0. If beta is 0, it is nothing but an is equal to alpha by gamma times an minus 1, which is nothing but a GP, which is obvious. And again, if gamma is equal to 0, an is a constant. We want to solve this recurrence with all these constraints. That is why we don't want any of them to be 0. Now in order to solve this, we'll make a clever observation. What we'll do is we'll take the reciprocal on both sides. We'll get 1 by n is equal to beta an minus 1 plus gamma by alpha an minus 1. This will imply 1 by n is equal to beta by alpha plus gamma by alpha times 1 by an minus 1. Now what I'll do is I'll call Vn is equal to 1 by n. I'll get Vn is equal to gamma by alpha times Vn minus 1 plus beta by alpha. Now if I call this some, let's say C1, and this is C2, it is exactly of the form that we have seen before and we know how to solve it. So therefore if we solve it, we will get Vn, and we take the reciprocal, we get the solution for An. I hope everyone understood. Now let's move on to the next one. The next one is just a more generalized version of the previous one. It says An is equal to alpha n minus 1 plus beta by gamma n minus 1 plus delta. The constraint is the denominator is not equal to 0 for all n greater than or equal to 2, and alpha by gamma is not equal to beta by delta. What will happen if they are equal? Alpha by gamma is equal to beta by delta. Let's equate it to some k. We get alpha is equal to k times gamma, beta is equal to k times delta. If you substitute this in place of here alpha and beta, we will get An is equal to k times gamma An minus 1 plus delta divided by gamma An minus 1 plus delta. Now these both terms will be cancelled and we'll have An as a constant sequence, which we don't want. We want, that is why we are putting an unequal, not equal sign in between, and we also don't want a1 to be equal to alpha a1 plus beta by gamma a1 plus delta, because if I put n equal to 2, I'll get alpha a1 plus beta by gamma a1 plus delta, which is be nothing but a1. a2 will be equal to a1. Similarly, I'll get a3 equal to a2, and so on. The sequence will be a constant. So that is why we put this restriction. Now since the constraints are clear, let's solve this. And also this type of recurrence, nonlinear recurrence relation, is known as Riccati sequence. The previous one was just a special case when beta is equal to 0. Now in order to solve this, we'll use the method of substitution, and we'll try to convert it into any of the forms that we learnt before, so that it will be solvable. So let's see how we can do that. What we'll do is, we'll call An is equal to Bn plus lambda. Again, lambda is an arbitrary constant which I'll be choosing later. If I substitute this definition, I have An is equal to alpha An minus 1 plus beta by gamma An minus 1 plus delta. Now if I substitute this Bn definition, I'll get Bn plus lambda is equal to alpha Bn minus 1 plus alpha lambda plus beta divided by gamma Bn minus 1 plus gamma lambda plus delta. Now I'll take this lambda to the other side and take LCM. I'll get Bn is equal to alpha Bn minus 1 plus alpha lambda plus b minus lambda times gamma Bn minus 1 plus gamma lambda plus delta divided by the denominator, gamma Bn minus 1 plus gamma lambda plus delta. Now what we'll do is, we'll segregate Bn minus 1 terms to the other side and the constants to the other side. We'll have alpha minus lambda gamma times Bn minus 1 plus alpha lambda plus beta minus gamma lambda square minus delta lambda divided by gamma Bn minus 1 this gamma lambda plus delta. Now if I choose a lambda such that this expression becomes 0, then I'll have bn is equal to constant times bn minus 1 by the constant bn minus 1 plus gamma lambda 1. Lambda 1, let's say it's root, plus delta, which is nothing but of this form. So that is why we'll solve this quadratic and equate it to 0. We'll get two roots, lambda 1 and lambda 2. We can choose any of the roots. Let's say if I choose lambda 1, I'll get bn is equal to alpha minus lambda 1 gamma times bn minus 1 divided by gamma bn minus 1 plus gamma lambda 1 plus delta. Now this is of the previous form. I can take the reciprocal, divide the terms, and then substitute 1 by bn as some new sequence, and then we can solve it. So this is how we deal with the method of substitution. We can also solve this using another method of fixed point. Let me show you how the method works, and then let's discuss about it. Now we have an is equal to alpha an minus 1 plus beta by gamma an minus 1 plus delta, all those constraints applied that we took in the question. Now what we'll do is, we'll substitute all this an terms with something like x. X is equal to alpha x plus beta by gamma x plus delta. Now if we simplify this, we'll get a quadratic equation like gamma x square plus delta minus alpha x minus beta is equal to 0. Now this will have two roots. Let's call them as p comma q. Now what we'll do is, we'll define a new sequence bn is equal to an minus p by an minus q. Now instead of these an's, we'll substitute the definition of an that we have. We'll get bn is equal to alpha n minus 1 plus beta by gamma n minus 1 plus delta minus p divided by alpha n minus 1 plus beta by gamma n minus 1 plus delta minus q. Bn is equal to, now I'll take the LCM and this denominators will be cancelled. We'll get alpha n minus 1 plus beta minus p times gamma n minus 1 minus p delta divided by, I'll get the same thing in the denominator but where p is replaced with q. Alpha n minus 1 plus beta minus q times gamma n minus 1 minus p q. Q delta. Now what we'll do is, now we have the quadratic here. From here we'll say that beta is equal to gamma x square plus delta minus alpha times x. Now since p and q are the roots, we can substitute p and q in place of x. Now here we have beta, right? Now in each place of the beta we'll substitute this equation. In the numerator, since we have p terms, I'll write it in terms of p, and in the denominator I'll write it in terms of q. I'll have bn is equal to alpha n minus 1 plus gamma p square plus delta p minus alpha p minus p gamma an minus 1 minus p delta divided by alpha n minus 1 plus gamma q square plus delta q minus alpha q minus q times gamma n minus 1 minus q delta. Now we can cancel these terms and we'll do grouping in the other ones. What we'll get is, what I'll do is I'll group this term with this and this alpha term with this. Similarly in the denominator I'll get bn is equal to alpha times an minus 1 minus p minus delta p times an minus 1 minus p, and similarly in the denominator I'll get alpha times an minus 1 minus q minus delta q times an minus 1 minus q. Now I'll take the an minus 1 p minus p in the numerator common, in the denominator this term common. I'll get bn is equal to an minus 1 minus p by an minus 1 minus q times alpha minus delta p by alpha minus delta q. Since this is a constant, we will call it some k. And if you notice, we have bn is equal to an minus p by an minus q. Now if you notice, this is nothing but the before term of this sequence, which is bn minus 1. bn is equal to bn minus 1 times k. Now I'll get bn is equal to b1 times k power n minus 1. And now if I substitute bn, I'll get an minus p by an minus q is equal to b1 times k power n minus 1. Now if I isolate for an, I'll get an minus p is equal to an times, now an times b1 into k power n minus 1 minus q times b1 into k power n minus 1. Now from here I'll get an is equal to p minus q into b1 times k power n minus 1 divided by 1 minus b1 times k power n minus 1. This is our closed form solution for an if we use this method. You know what p and q are? P and q are the roots. K is nothing but this value. So this is our solution. Now when we started, I took an and an minus 1 to be x. Now this x has a special name. It is known as the fixed point of the sequence. Though the name suggests that it will, like, since it's the fixed point of the sequence, we will think that maybe this value will be achieved at some point in the sequence. But no, this value is not achieved in this case, because if something like a fixed point occurs, then the sequence will become constant from that point. It's not possible for the sequence to become constant suddenly. So therefore we can say that this x will actually never be achieved. Then why did we do this? We took an and an minus 1, replaced them with x. We got a quadratic. We took roots p and q and then defined this new sequence. And then you saw that the terms have beautifully cancelled and we have got a GP. It's not a very simple manipulation. Like you can't just come up out of thin air and say that this is the manipulation we are doing. But the idea behind this manipulation is not that simple for us to understand in the high school level. So therefore, for now, we'll look at this like an elegant method to solve the recurrence relations of this type. I hope everyone understood. In the next video, we'll see some more solving techniques, and we'll also discuss about second order recurrence relations and then move on to problem solving. Thank you. Take care. Goodbye.